In this video series, we're looking at categorical data analysis, and I'm going to take on another example now. The primary difference in this example and the previous example is that we're now going beyond two groups. Specifically, we're going to go to three groups, but the same principles are going to apply whether you go to 4, 5, or even more groups. And we're going to look at more than two response categories. So now we're going to have three response categories. And again, this example is going to be the same even if we had 4, 5, or more response categories. So in general, we're now going to consider a J by K factorial design where there are J categories or levels of the explanatory variable and K categories or levels of the response categorical variable. This is a hypothetical study. 60 teachers were randomly selected from each of three populations: those that had no teacher training, those that had some teacher training, and those that had much teacher training. Trained observers watched the teacher handle misbehaviors in the classroom and then classified each teacher as being primarily punitive, reasoned, or evasive in their approach to bad behavior. Now, of course, there's a lot of things going on in this study that go beyond statistics. There are a lot of measurement issues. What do we mean by punitive behavior? Or what do we mean by reasoned behavior? Are these raters who are watching these behaviors in the classroom, are they rating these behaviors the same from one rater to another? Would two raters both rate reasoned or both rate punitive, or might they differ? That has to do with inter-rater reliability, which is a measurement issue. So all of the statistical analysis that we have been going through in this course and any previous course you had relies heavily on design issues that are outside of the realm of statistics, measurement issues that are outside the realm of statistics, and we're focusing primarily on the data analysis, assuming that we have good data. But that's a big assumption. That's a big what if. And so what if these data were not in fact valid? Well, then that would invalidate what we're going to do. So we're going to have to assume that we're looking here at an example in which we have valid observations. Now note the numbers here are not quantities of the response measure, but frequencies for each response level. So in the no training condition, we have 27 individuals who were classified as punitive. We have 19 that were classified as reasoned and 14 classified as evasive. So that is looking at only one level of the explanatory categorical variable, that is how much training the teachers had, and we just looked at all three levels of the response categories, which are what kind of approach do they have to misbehaviors. So we could say the same, of course, for some training. We could go through those and much training, but hopefully you get the idea. So if you wanted to know the sample size in this study, you would just add up all these frequencies that you're seeing in front of you here. All right, let's enter the data into an R notebook. I've set this all up so that you don't have to watch me type. The data, again, are in summary form. What we have are the frequencies given to us here for each of the categories of the explanatory variable and each of the categories of the response variable. So since they're in summary form, I can go ahead and put them all into a matrix. This time I have three columns. So I'm entering the data, and I'm entering it in three columns. And note that I also use a by row equals false argument here, which indicates I'm going to be entering by column. So if you look at the 27, 19, and 14, that should be for the first column. And indeed, that's what we see here, 27, 19, and 14 for the first column. So I'm entering them in by column. I'm going to create the column names, which are going to be none, some, and much for the three teaching conditions of the explanatory categorical variable. And the row names punitive, reasoned, and evasive for the 3 levels of the response categorical variable. I'm then going to turn this into a table, and we're going to look at it. And so when we do it, this is what we actually obtain. Now, what are the proportions that are of interest here? As we look back at these frequencies, what are we looking at in terms of proportions, and what proportions would be equal under the omnibus null hypothesis of proportional equality? There are various ways we could calculate proportions. We could calculate it out of the total. We could calculate it out of the column. We would call those conditioned on the column, or we could condition on the row. Which one do we want here? I'm going to pause just for a moment, let you think about it, and then I'll answer that. If you said we want the proportions conditioned by column, that's correct. That is, I want to know in the no training condition what proportion of the teachers are punitive. I want to know in the some training condition what proportion of the teachers are punitive. And in the much training, what proportion of the teachers are punitive. If the amount of teacher training has no bearing on what proportion of the teachers are punitive, then those 3 proportions that I just named should be all equal. Similarly for reasoned, they should be all equal. The no training reasoned proportion, the some training reasoned proportion, and the much training reasoned proportions. So I want column conditioned proportions here. So back in my R notebook, I'm actually using 2 because 1 is for rows, 2 is for columns, and that will give me the column conditioned proportions. Now, descriptively, as I look at this, I see that it looks like the omnibus null hypothesis is not true. At least from a descriptive standpoint, it looks like it's not true. But remember, the omnibus null hypothesis is about the comparison of pies, that is, the proportions in the population. And we're not looking at those. We're looking at the proportion in the sample. Can we say, from the differences we're seeing here in the sample, do we have enough evidence to be able to infer outside of that study? We'll get to that when we talk about inference. But right now, descriptively in the study, it's quite clear that there are differences. 45% of those in the no teacher training condition were punitive in their response to misbehaviors, whereas only 18% with some teacher training, and even less, about 12% of those with much teacher training. 32% of those with no teacher training were reasoned, whereas it was 47% with some, and almost 2/3, 63%, with much teacher training. In terms of being evasive, it was 23% with none, 35% with some, and 25% with much teacher training. Not as stark of a difference there among those with evasive as we saw with the punitive and the reasoned. But the omnibus hypothesis, because it's omnibus, is asking the question, is the proportion of punitive the same? Is the proportion of reasoned the same? And is the proportion of evasive the same? It's asking about all 3 of those possible responses if they're the same across all 3 levels of the explanatory categorical variable. In the sample, the answer is no. We see distinct differences and we could describe them. The more teacher training there is, the more reasoned the approach to misbehavior. The less teacher training there is, the more punitive the approach to misbehaviors. Let's look at this as a picture. I normally look at pictures first and then the statistics, but notice that we need it to actually calculate that teach prop object. We needed to calculate those descriptive statistics before we could actually create the bar plot. So that's why I'm looking at it the other way around. Although if I was writing a report, I might put the bar plot first and then these descriptive statistics. Here's the bar plot. And we're seeing the exact same thing we saw in the descriptive statistics, but graphically, we're getting a general impression quickly, whereas the descriptive statistics require us to think a little more, but they have the advantage of being to drill down to specifics. So when I look at this, I notice right away all the black there is in the none category, and that's the punitive category. I notice all the pink there is in the much teacher training category. That's the reasoned. And I know there are more similarities in the evasive category. So those are our descriptions. From those descriptions, we can actually say that there are differences, and we can report those regardless of what we see later on with inference. We can report these differences in our research report. We don't have to just report inferences. In fact, I would prefer that you focus on description first and foremost. And then when you see something that is important, see if you can make inferences. And here I see something important. I see that as you increase teacher training, you seem to be leading these teachers to a more reasoned approach to dealing with misbehaviors. So moving on to inference, the conditions we have for valid inference are independence of our observations within groups. So that means that in the no teacher training group, all these participants in our study need to be independent of one another. That's a design characteristic. And we also have to have independence across groups so that teachers in one group don't appear in other groups. That's probably implied by this study. How can you be in the no teacher training condition and the much teacher training condition at the same time? You can't. So I think that independence is implied by the nature of our study. But then we have to look at expected frequencies. So to do that, I'm introducing another function that we can use, and that is the chi-sq.test function, and I'm applying that to my teaching table and saving the results. The reason I'm saving the results is that when we do this, that we get a whole bunch of possibilities here under cat test. I have a whole bunch of possible things I can look at, and notice one of the things I can look at is expected values. So I'm going to print out these expected values here, cat test expected. I'm going to put those on the screen. And when I put those on the screen, I notice that I have this set of expected values. Those are expected under the null hypothesis. That is, this is what I would expect to get if in fact there are no differences amongst the conditions. So I would expect to get 15 people in the none, 15 in the some, 15 in the much. Now, why are those the same? Why are those all 15? Well, if you go back to the original study, it says 60 teachers were randomly selected from 3 populations. So because we have equal frequencies, we also have equal expectations in our group. How are those expectations calculated? We take the overall punitive, that is adding up the 27, 11, and the 7, and then we divide that by 180. There are 60 teachers in each of 3 conditions, so that's 180. And so if you divide the 27 plus 11, that's 38 plus 7 is 45, divided by 180, 45, the number in the punitive, divided by 180, the total sample size, that's 0.25 or 25%. So therefore, if the homogeneity hypothesis is correct, our best estimate for each of the no training, some training, and much training categories is that 25% of the participants in that category will be punitive. And so in the no training condition, that would be 25% of 60, which would be 15. In the some training condition, 25% of some training would be 25% of 60, 15, and 25% of much training, again, 25% of 60 or 15. So here are our expected frequencies. The null hypothesis is that the type of response to misbehavior is not related to teacher training. If this hypothesis is correct, we expect the same proportion of punitive teachers in each training condition, the same proportion of reasoned teachers in each training condition, and the same proportion of evasive teachers in each training condition. The best estimate of the population proportions can be calculated by using the proportion in each response condition combined across teaching categories. Now, that would not be the best estimate if there are differences in the amount of punitive, for example, in no training and the amount of punitive in some training. If we knew that there were no differences, then we wouldn't take the margins. But we're calculating this under the null hypothesis, and that's what allows us to test the null hypothesis. The question becomes, in these expectations that we see here, are they much different than the observations we see here? So we're in essence comparing this table of what we observed to this table to what we expect under the null hypothesis. And the further away you get from what we expect under the null hypothesis, the least probable it becomes. You know that if we were to do another sample, we would not get these same observed results. We'd get different results. There is sampling fluctuation. The question becomes, are these so much different than what we expect under the null hypothesis that we can say these come from more than just sampling fluctuation? They also come from true differences between the no training, some training, and much training conditions. So coming back here to where I calculated those expecteds, remember we're talking about the conditions for valid inference. What do they have to be? Well, we have to be at least 5 in at least 80% of our cells. We're over 5 in 100% of the cells. And we can't have any cell less than 1 in our expected frequencies. None of them are less than 1. So these are all fine. So now we can do the omnibus test. And I'm going to go ahead and use what I calculated up here using the chi-square test function and stored it in cat test. I'm just going to show you that. And that gives me the p-value. Remember last time, in the last example, I used the summary function, and that gives me the same thing, the same p-value. So both of these will give you x squared and the p-value based upon comparing x squared to a chi-square distribution with 4 degrees of freedom. You'll remember that the parameter of a chi-square distribution is simply the degrees of freedom. That distinguishes from one chi-square distribution to another. Here we have 4 degrees of freedom. Why 4? Well, remember we take the number of categories in our explanatory variable, that would be 3, none, some, and much, and subtract 1, that gives me 2. The number of categories in our response variable, punitive, reasoned, and evasive, that's 3, subtract 1, that's 2, and then we multiply. 2 times 2 equals 4. So that's what gives us this 2 degrees of freedom. When I now look at 23.03 on a chi-square with 2 degrees of freedom, I see it's way out there in the tail. Thus, I'm going to reject the omnibus null hypothesis. That's my decision to reject the omnibus null hypothesis and conclude there are differences in these various conditions. Can we say that the teacher training caused? Well, let's look back at the example. Notice we sampled from each of 3 existing populations. So we cannot say that it caused. Why not? Because there might be confounding variables. There might be something that goes into a person and a personality that would lead them to seek much teacher training versus someone who takes perhaps an alternative path and gets into teaching without any formal education, perhaps takes an alternative certification route. And so because these other variables could exist along with the training, we can't say that there is a causal difference, yet we can say that we can reject the omnibus hypothesis of proportional equality, that is, the proportions being equal for punitive, the proportion being equal for reasoned and the proportion being equal for evasive in all three of the conditions, we can reject that omnibus null hypothesis. When we reject an omnibus null hypothesis, it could be valuable to look at specific comparisons, and so that's what we'll do in the next video.